this video, we're going to take a look at section 5.2 on binomial probability distributions. So in 5.1, we discussed just generically the concept of a probability distribution. In 5.2, we're going to look specifically at the binomial probability distribution. In order to be considered a binomial probability distribution, the situation has to meet these four requirements. The first requirement is that the procedure that you're running has a fixed number of trials. So for example, maybe we are going to decide to flip coins. And so the procedure we might run is to flip a coin 10 times in a row. So 10 would be the number of trials that we are running in that procedure, right? We can't change that the next time to 15, right? If we decide we're going to flip the coin 10 times, that's our procedure, and we have to stick with flipping the coin 10 times. We can't change it from procedure to procedure. So that's what it means by the trials being fixed. The trials must be independent. Again, the coin flip example is a good example of that. So when I go to flip the coin the second time, the chance of getting heads or tails is unaffected by what I got the first time I flipped the coin, right? So when I'm flipping coins, each time I flip the coin, the result I get, the probabilities for that result are independent of the events that occurred before it. Each trial must have all outcomes classified into two categories. Again, flipping coins is a really good example of this. So when you flip a coin, you either get heads or you get tails. There's two outcomes there. We're going to be looking at some other scenarios in this section. It's pretty common to label the thing that you're counting the probabilities on to be the success. I don't know if counting is the right word there. Calculating maybe is a better word. Right. So whatever it is that you're calculating probabilities for, whatever event you're looking to happen for those probabilities is called the success. And the other thing that can happen is just called the failure. And while those terms have certain emotional connotations to them, we're not, don't apply those emotional connotations to these problems. So really, when I say something's a success, I'm not saying it's a good thing. And when I say something's a failure, I'm not saying it's a bad thing. So for example, another kind of binomial situation is when, parents are having children, either they have a boy or they have a girl. That's two outcomes. So if we're looking at the probabilities of, for example, taking 5 families that each have one child and finding the probability that 3 of them are boys, because we're calculating the probability about boys being born rather than girls, having a boy is what we would call a success in that scenario. That's the technical term we would label that because that's the thing we're calculating the probability on. So having a boy would be labeled the success, having a girl would be labeled a failure, but I don't mean anything by that. I'm not trying to say having a boy is good and having a girl is bad. Right? It's just the language, it's just the mathematical language that we use to label the thing we're looking for and the thing we're not looking for. But we don't mean anything good or bad by calling one thing a success and the other thing a failure. The last thing is that the probability of a success remains the same in all trials. And so the probability cannot change as we go from one trial to the next. And this is kind of related to requirement number 2, that the trials must be independent. But clearly, and I don't know what the scenario is, but in math, we always have to be on the lookout for, if we state these rules, is there some loophole that somebody could find that would violate these rules, but still, or not violate the rules, but satisfy the rules, but, create a situation that doesn't work, right? So if we're not careful in how we set up the rules, somebody could say, well, I'm following all the rules you set, but I'm still getting this kind of result and it doesn't match what you're saying. So we have to be very careful about all the rules we lay out. So there must be some scenario where you might have independent trials, yet the probability of a success might be able to change at some point as you're running the trials. I can't think of what that would look like, but maybe that's some kind of possibility. So because of that, even though it might be rare, we have to state both requirements. It has to be independent, and we have to make sure the success doesn't change as you go from trial to trial. So again, flipping coins is a good example. The probability of getting tails stays the same from the first coin flip to the 10th one, right? It's going to be 1/2 every single time. And so the probability of a success does not change. In that case, success meaning tails, right? Because that's the thing I was talking about calculating the probability of. All right, so if you meet those 4 requirements, then you have a binomial probability distribution. And also something I forgot to mention, I've restarted this video, like this is my 5th or 6th time. Not that I haven't really got too far into it. I don't know, I'm having some trouble just getting rolling here. So I already put that on the screen, but I forgot to mention it, that the number of trials is n. That's the variable we use to represent the number of trials. Okay, so let's consider this example. Determine whether or not the given procedure results in a binomial distribution. And so we will say, yes, it's a binomial distribution if it meets all 4 of those requirements. And we will say, no, it's not a binomial distribution if it fails any of them. So if just even one of those requirements is not met, it cannot be a binomial distribution. All right, so let's look at part A. Treating 152 couples with a fertility treatment and recording the gender of the 152 babies born to these couples. All right, so first requirement, are there a fixed number of trials? Yes, they fixed it at 152. They're looking at 152 couples, and as long as every time they run this procedure, it's 152 couples, it's meeting requirement number 1. Right, there's a fixed number of trials. In this case, it's 152. Requirement number 2, the trials must be independent of each other. And so we have to consider the situation that, let's say we take one couple and it turns out they had a boy. Does the first couple having a boy affect the probabilities of the second couple's gender, the gender of the baby? And the answer is no, it shouldn't, right? So whether or not the first couple has a boy or a girl should not affect the probabilities of the second couple having a boy or a girl. That's a good way to put it. And so there doesn't seem to be any indications here that these would not be independent. And so again, you could read into it somehow. You could maybe concoct a hypothetical scenario where somehow the gender of the first couple's baby affects the gender of the second couple's baby. I don't know how, but again, you could make up something. And then you would say, well, in that case, it wouldn't be independent. But again, with these kind of questions, you don't want to read any further into them than what's actually in the problem. Do not construct these hypothetical scenarios. If they wanted you to draw that conclusion from that, they would make it explicit in the problem. They would say, consider this situation, and then you would take that into account. But if they're not mentioning it, you shouldn't assume that it's going on. Right? So based on what's given in part A, nothing there seems to indicate that requirement number 2 would be violated. The gender of the babies for these couples should be independent of each other, right? The gender of one couple's baby should not affect the probability for the gender of another couple's baby, all right? And so requirement number 2 seems to be satisfied. Requirement number 3, there's only 2 possible outcomes. And that is the case here because we're recording gender. And so either the child will be male or female. So 2 outcomes there. And requirement number 4, the probability of a success should not change from couple to couple. Right? So the couples are the trials here. And so the chance of the first couple having a boy should be the same as the chance of the last couple having a boy or girl, whichever gender you want to look at. And again, based on the information given in this problem, that seems to be the case. Now, this is fertility treatment, and there may be methods for trying to increase the chance of having a boy or increase the chance of having a girl using these treatments. And so I'm not saying that the probability is 50-50 necessarily. Maybe the probability of having a boy is 60%, because maybe that's the gender that the couples are, wanting. But it should stay 60% for every single couple. If they're doing the same treatment, the probability should stay the same throughout. And again, you could maybe come up with some hypothetical scenarios where different couples might have different probabilities, but we're not given that information in part A, so we shouldn't assume that information. And so based on the requirements for a binomial distribution and what's actually given in part A, it seems to satisfy all 4 of those requirements. So part A is a binomial distribution. I'm just going to put binomial here. All right. Now, part B. And so maybe I should have did part B first so you can see how obvious it's going to be if it doesn't work. Treating 863 subjects with drug A and asking each subject, how do you feel? Now, is there a fixed number of trials? Yes, right? There's 863. So requirement 1 is satisfied. It's a fixed number of trials. Number 2, are the trials independent? Yes, they should be independent. The first subject saying, I don't feel so well, shouldn't cause the second subject's probability of saying that to go up or down. Because we're going, I mean, again, not to read into it too much, but like, I would assume they're asking these people separately. Now, if they're all in the same room and they get to hear each other's responses, then no, it's not independent, because what somebody else says might make you reflect on your situation and it might change what you say, right? And so if you're all in the same room and you're hearing each other's responses, then no, they would not be independent. So again, under that hypothetical scenario, you might say no, but we weren't told that that was the scenario. And so I'm going to assume that the responses that one person gives will not affect the responses of the other people. And so they should be independent. So 2 is actually satisfied. And you might say, I thought you said this was obvious. Well, here's where it's obvious, right? I'm just going through the numbers in order. 3, there's only 2 possible outcomes. That's what's required for it to be a binomial distribution, and that is not satisfied here. If you're asking, how do you feel? There are multiple ways to respond to that. I feel good. I feel bad. I feel okay. I feel, 90%. I feel 80%. I feel 70%. I feel 100%. So I don't know how you would, there's multiple ways somebody might answer that. And if that's the way you're asking it and that's the response you're recording, there's more than 2 possible responses to that. And so this one is not satisfied. There's more than 2 outcomes. Now, if they would reframe the question to say, are you feeling good or bad? Then you can switch it back to a binomial situation, right? But that's not the way they worded it. So if these scientists needed this to be a binomial or wanted it to be binomial just to make the math easier, because you'll see with binomial distributions, we have some shortcuts we can use. It makes the math a little easier to calculate probabilities and things like that. Then they could reword the question or change how they record the response. And so they could still ask, how do you feel? But then maybe they only have 2 checkboxes, positive or negative. And if they respond positively, you check that. If they respond negatively, you check that, right? You could try to force it to be 2 possible outcomes. But again, that's getting too hypothetical about it. I'm reading into the question a lot further than what's actually given. So based on what's given in the problem, it seems like there's more than 2 outcomes. And so this is not binomial. All right. So they're not going to try to hide it from you. Whatever requirement's not being met, it should be obviously stated somewhere in the problem. It shouldn't be something you have to concoct a crazy scenario in order to violate the requirements. All right. Okay. Here's some notation for binomial probability distributions, and some of these don't really get used. Like, for example, this first one, you might use S to represent a success, F to represent a failure. And that would be fine, because then you could say, well, the probability of a success you could represent like this. But we actually have another representation for that concept, which is this, right? So the probability of a success, instead of writing it with this function notation, we're just going to call that lowercase p. So p is the probability of a success. Q will be the probability of a failure, right? So this is going to be the probability of a failure, Q. And because there's only 2 outcomes, these are complements of each other. Either you have a success or you have a failure. And so because of that, we can use the rule of complements to calculate this. So the probability of a failure is 1 minus the probability of a success in any one trial. Now, when I'm talking about the probability of a success or a failure, I'm talking about not for the whole procedure, but when you take one trial of that procedure. The probability of a success on that one trial is P. The probability of a failure on that one trial is Q. N, as I already mentioned, is the fixed number of trials. And then we use X as our random variable to denote the number of successes out of those N trials. So going back to my earlier example, if I'm going to flip a coin 10 times, N would be equal to 10. And then I might say, what's the probability of having 6 tails out of those 10 coin flips? 6 would be the number of successes out of the 10 coin flips. Right? So X would be equal to 6. I'm looking for 6 successes out of 10 trials if I'm asking what's the probability of getting 6 tails out of 10 coin flips. And so P of X represents the probability of getting X successes out of N trials. And that's really ultimately what you're going to be asked to find in these problems is, given this scenario, what's the probability of having this many successes out of this many trials? And there's a formula to calculate that. And not only is there a formula, that formula is encoded in your calculator. And so you can just use a function on your calculator which will use the formula for you. So you won't even have to directly use this formula. It's embedded in your calculator. You just have to know where that function is in your calculator. You input the information, the calculator runs the calculation for you. But what's nice about this binomial distribution is that there is a formula that describes how to find the probabilities. We don't have to use a chart. We don't have to use a table anymore. There's a formula. You just plug the numbers in and you get the answer. And so it's very customizable, right? You know, for whatever N is equal to, whatever X is equal to, the formula can handle lots of different inputs there. We can have 10 coin flips. We can have 20 coin flips. We can have 6 tails. We can have 8 tails. We can have 1 tail, right? We can try different numbers there, and the formula can accommodate all those different scenarios. You just plug the different numbers in, you get the answer either way. Instead of having to have different charts each time, right? Because without the formula, we would have to have one chart for 10 coin flips, one chart for 20 coin flips, one chart for 15 coin flips. We'd have to, because every time it's a different probability distribution depending on how many times you're going to flip the coin. The formula prevents us from having to approach it that way. All right. So let's take a look at the next screen. I didn't really review my notes beforehand. Maybe that's kind of why I was having trouble getting started recording this video. I should have reviewed things. So here's the formula, which you're more than welcome to use yourself. But I would recommend just using the function in the calculator. But I wanted to at least show you what the formula looks like, and maybe explain why the formula looks the way it does, just real briefly. So going back, and maybe 10 coin flips is a little bit extreme for the example that I want to talk about. So let's look at 5 coin flips. I think 5 would be okay. Hopefully not, it doesn't get too out of hand. So let's say we're going to flip a coin 5 times. So n is equal to 5. The probability of flipping the coin and getting tails is 1/2, or 0.5 if you want to write it as a decimal. So I can represent that with the lowercase p, right? That's the lowercase p is the probability of a success on any one trial. So when I flip the coin one time, the probability of having a success when I flip that coin is 50%, 1/2, 0.5. And the success in this case is getting tails. All right. So what I could ask is, what's the probability that if I flip a coin 5 times, that I get 3 tails out of the 5 coin flips? Now, without this formula, it's a pretty tough calculation to do. Now, you could try to think of, well, how many different outcomes are there when I flip a coin 5 times? Right. So the way I like to represent those, because counting the number of possible outcomes is also not as simple as you might think. I imagine a lot of students might guess like 10, because there's 2 outcomes each time. You're flipping it 5 times. Maybe there's 10 different possible outcomes. It's bigger than that. And so there's actually a pretty cool method for adding up all the different ways something can happen in a situation like this. And I say adding up, but it's actually going to involve multiplication. So what I like to do, and this is the way I remember being taught, I took this one class, and maybe one of my first steps into the bigger world of mathematics. And I'm not trying to brag or anything, but your first couple of years of math are fairly limited in scope. and very regimented. There's just a particular path everybody has to follow, which is, algebra to trigonometry to calculus to differential equations. If you make it that far, that's really the path everybody takes first. And then if you want to go further with math, often after differential equations, you take linear algebra, which is a different kind of algebra. But after that, it opens up. And there's different branches of math that you can, explore. And one class I ended up taking just on a lark was a class on discrete mathematics. I didn't even really know what that meant. But we've talked about the word discrete in this class, so you guys probably have a better understanding of it than I did when I took that class. But one thing we spent a lot of time doing in that class, which I really found fascinating, was trying to count things. And I know it sounds kind of silly, right? Because you learn how to count in kindergarten. But we're talking about like complicated scenarios with large numbers of things and trying to count how many ways can you arrange these things in a certain order? How many ways can these people be seated in this room? How many ways can you flip a coin 5 times? And how many different outcomes can you get from flipping a coin 5 times? And the method that teacher presented to me was to represent the different trials or events or whatever with just a horizontal line like this. Right? So that's my first coin flip. And the way I imagine it is whatever you actually end up getting, you would put here. So if you flip the coin and you got tails, you put T here. If you flip the coin and you got heads, you put H here. But it doesn't really matter what you end up getting. We just want to have some way of indicating this is the first trial and we'll get some result from that. And this is the second trial. We'll flip the coin again and we'll get some result from that. Third trial, fourth trial, and we're going to flip the coin 5 times. And then underneath, so not on top where you would actually write the results from your, procedure, but underneath, you're going to write the different possibilities for each of those trials. So when I flip the coin, there's 2 possible things that can happen. That's, again, it's binomial, so that's the way it needs to be. So there's 2 things that could happen with the first coin flip. I could either get heads or tails. There's 2 things that could happen with the second coin flip, heads or tails. 2 things with the third one, 2 things with the fourth one, 2 things with the fifth one. And then to add up all the different possible outcomes from flipping a coin 5 times, you multiply these together. And so that's going to be 2 to the 5th power, which is 32. Right? So maybe a bigger number than you might have expected. There are 32 different possible outcomes from flipping a coin 5 times. I was thinking 10 you might guess, but another one you might guess is with only 5 different outcomes there. I don't know, maybe not. Yeah, 10 probably would be a common guess, but it's actually 32. Oh, you might guess, well, how many different outcomes are there? Well, you can get 1 tail, you can get 2 tails. So you might guess like 5 or 6 different outcomes, but no, there's a lot more than that. There's 32. All right. Now, we're interested in getting exactly 3 tails out of our 5 coin flips. Right. So one way of that happening would be to have tails on our first coin flip, tails on the second coin flip, tails on the third coin flip. And that's it. Now, because we're talking about exactly 3. So if I got tails again and tails again, let's say I got all 5 tails. You might say, well, you got 3 tails, but you got 5 tails in this case. That doesn't match this description. This is asking the probability of getting exactly 3 tails. Excuse me, I don't know what I'm trying to say there. This is the probability of getting exactly 3 tails, not at least 3 tails, right? There's a big difference there, right? At least 3 tails would mean, okay, this would count too, right? You have at least 3 here as well. We want to know the probability of getting exactly 3. So this wouldn't register with that. This doesn't match that probability that we're trying to calculate. So one way of getting 3 tails would be, this is what I was going to put the first time, tails, 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 then heads, then heads. That's exactly 3 tails, right? This is 5 tails, so it doesn't count. This is 3 tails. So that matches this description. And you could find the probability of this. It's a multiplication rule situation, right? So if I wanted to find the probability of getting tails, 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 heads, heads, all I would have to do is multiply. This is the probability that the first coin flip is tails, times the probability that the second coin flip is tails, times the probability that the third coin flip is tails, times the probability that the fourth coin flip is heads, times the probability that the fifth coin flip is heads. It's a sequence, right? We need the first one to be tails, and then the second one to be tails, and then the third one to be tails, and then the fourth one to be heads, and the fifth one to be heads. It's a sequence, therefore it's the multiplication rule. And so you would take the probability of tails, times the probability of getting tails, times the probability of getting tails for the first 3 coin flips, times the probability of getting heads, times the probability of getting heads. Right? Now, we know the probability, and this is maybe a bad example for this reason, the probability of getting tails or heads is 1/2. So these 3 will all be 1/2, and these 2 will also be 1/2. So it makes it hard to distinguish between the ones that we're getting from tails and the one that we're getting from heads. So instead of putting 1/2 there, I'm going to use p, lowercase p, right? P is the probability of getting that success, right? T is a success in this case. So this is the probability of getting a success, which we can represent with p. And then this one's also p, and this one's also p. Heads, in this case, is a failure. And so this is the probability of getting a failure, which I represent with q. And if I'm going to multiply these all together, we have 3 p's being multiplied together. So that's going to be p to the 3rd power. And we have 2 q's being multiplied together. And now you can see why this formula has those 2 factors in it. So if you want to find the probability of 3 successes out of 5 trials, you're going to have the probability of a success 3 times and the probability of a failure twice. I don't know why I'm having trouble talking right now. All right. And so that's where these come from. So if you have 3 successes, you'll have p multiplied to itself 3 times, which will be p to the 3rd power. So remember, x is representing the successes. So this is p raised to the power of the number of successes that you're looking to happen, right? This is q raised to the n minus x power. This is just the number of trials left over that are failures, right? If you're going to have x successes, this is how many failures you're going to have. So this is the number of failures. Let's do that. Number of failures. This is the number of successes. Oops, I don't know how to spell success, evidently. Oh, I hit the wrong button. Okay, I'm going to have to erase now. Sorry about that. I tried to undo, but again, the undo and the previous page button are a little too similar looking. Number of successes. Let's spell it right this time. All right. So you're taking p to the power of the number of successes, just like we saw happen down here. Let's switch to a different color. Right. P to the 3rd power, because we wanted 3 successes, right? X was equal to 3 here. Okay, let's try to undo that one this time. 3. And then 3 is what we ended up getting down here. And then q to the power of 2, that's the probability of a failure raised to the power of the number of failures that you're expecting to happen. If you want 3 successes, you're going to have 2 failures if you have 5 trials altogether, right? And the way you calculate that is to take the number of trials, which is 5, minus the number of successes you want, and whatever's left over, that's the number of failures that you have to have, right? So 5 minus 3, and that gives us this part of the formula. Now you might be saying, okay, that explains p and q here and the exponents that you have. But what about this first factor? What's going on with that? This is called a combination. So as I mentioned, when I wrote this down, this was only one way of having 3 tails out of 5 coin flips. There are other ways. So this is only one way that we match this event, having 3 tails. You could have the first 3 be tails and the last 2 be heads. But there are other ways, right? So here's another possibility. We could have tails, tails, heads, tails, heads, right? That's also 3 tails. So that's also what I'm looking for. It's a different outcome. It's not the same as this outcome here because it's in a different order. And so it's another thing. It's another way of having 3 tails out of 5 coin flips. So we need to also add that probability in. So the probability of this particular thing happening is this. What about this one? What's the probability of this happening? Well, it's going to be the same. It's just in a different order, but this will be the probability of tails times the probability of tails times the probability of heads times the probability of tails times the probability of heads. And again, instead of using 1/2 because they're all equal to 1/2, we'll use P's and Q's here. This is going to be P times Q times P times Q. So again, even though it's in a different order, when you simplify this, you'll have P multiplied to itself 3 times and Q multiplied to itself twice, the same that you had up here, right? So this probability is also equal to P to the third power, Q to the second power. Now we have 2 of these, right? And so we have to add these together because it's an OR situation, right? Now here, this is an AND situation because it's tails first and then tails second and then heads third. That is a multiplication rule, and that's just for that particular calculation. But the probability of getting 3 tails, it could be tails, 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 heads, heads, or it could be tails, tails, heads, tails, hail. I said the wrong thing. I don't know, just making up my own syllables. I don't know what's wrong with me today. All right. It could be tails, tails, heads, tails, heads. That's what I meant to say, which is this particular sequence of events. And it could be 3 tails. So this is another way it can happen. So it could either happen like this, or it could happen like this, or it could happen as tails, heads, tails, heads, tails. That's another way it could happen, right? And there's more. But they're ORs, which means we should be adding those probabilities together. So far we have 2 of these. We have 2 P to the third power, Q to the second power. But we're going to add more to that. So how many are we going to have all together? That's what this thing calculates. This N choose X. This is called a combination, which is something your calculator can also do. And the way we would type it into our calculator, it's a really weird function to type into your calculator because you have to put a number before it and a number after it. So normally, if you're trying to do something in your calculator, you pick the function you want to use and then type everything in after that function. After you call that function, you type in all the inputs. But this function, you have to have an input before you call it and an input after you call it. So the way we would word this is 5 choose 3. Right. And this is going to tell us how many ways can we have 3 successes arranged out of 5 trials. Right? How many ways can we have 3 tails and 5 coin flips? This counts it for you. This is a counting thing. And there's actually a formula for this if you want to know what it is. And it involves another mathematical thing. So it's let's see if I can remember. It's n factorial. So it's an exclamation point, right? N exclamation point. And I always like to make the joke that it's not because we're excited about it, but it's because it's a mathematical function. It's the factorial. And that's the notation that I don't know how that got decided, but the exclamation point is the notation to indicate a factorial. Over, so I should be putting this up here actually. N factorial over, let's just erase this down here, over x factorial times n minus x factorial. So a lot of factorials. Now what is a factorial? Well, for example, we're going to get here 5 factorial because n is equal to 5. So we'll plug in 5 here for n. And that means you take 5 times 4 times 3 times 2 times 1. So a factorial just means starting with that number, multiply that number and every whole number, every integer below it down to 1. So 5 factorial means 5 times 4 times 3 times 2 times 1. 10 factorial would be 10 times 9 times 8 times 7, all the way down to times 1. Right? So hopefully I'm describing that correctly. So you take that number and every whole number below it down to 1 multiplied together. That's what the factorial notation means. Right? X in this case is equal to 3. Right? So we're going to have 3 factorial here. And then n minus x, that's going to be 5 minus 3, which is going to give me 2 factorial. So what I always remembered about this pattern here for the combination formula is that these 2 numbers should add up to this number. Right? 3 plus 2 gives me 5. So whatever x is equal to, I put that here, and then I put whatever number needs to be here so that these add up to the number on top. And so on the bottom, we're going to have 3 factorial, which is 3 times 2 times 1. That's the 3 factorial, times 2 factorial, which is just going to be 2 times 1. And you'll notice that things can cancel out. So instead of having to type all this into your calculator, you can cancel some things out. So the 3's cancel out here, the 2's cancel out, the 1's cancel out. Of course, the 1 doesn't really do anything, but so what do I have left on top? I have 5 times 4, which is 20, over 2 times 1, which is 2. 20 divided by 2 gives me 10. So without having to actually identify all 10 of them, I know from this calculation there are 10 different ways to flip a coin 5 times and have 3 tails. Exactly 3 tails, right? So there's, I didn't mean to word it, I don't know, that wording came out a little bit backwards to me, but what I meant to say was there are 10 ways to get 3 tails out of 5 coin flips. There's 10 ways to rearrange the order of the tails and the heads where you still have 3 tails and 2 heads, right? There's 10 ways to do that. I identified 3 of them here, but there's 7 more, right? And that would take a while to actually find them all, right? So if you're going to have to like manually count them, you have to list them out. Here's one way, here's another way, here's another way, and try to make sure you found them all. And that's the tricky part, because it gets confusing. And you might think, oh, I can't think of another one, but maybe there is and you just aren't seeing it. Or sometimes you put the same one twice, right? If the list gets pretty long, you might put the same one you already put up here and you're counting it twice. And so it's difficult. So this is a handy formula for counting the number of ways a thing can happen without actually having to list them out individually and count them that way. And so we're going to have not 2 of these, but we're going to have 10 of these p to the 3rd powers, q to the 2nd powers. And that's why the formula looks the way it does, right? And so in case you're curious, what's the answer? What is the probability out of 5 coin flips that you get 3 tails? It's going to be 10 times p is 1/2 to the 3rd power times q, which is also 1/2, right? The probability of getting tails is 1/2. The probability of getting heads is also 1/2. And so we raise the first one to the 3rd power, second one to the 2nd power. And so I'm going to multiply this out. So I'll have 0.5 to the 3rd power times 0.5 to the 2nd power times 10. And I'm getting 0.3125, right, as the probability, which is about 31%. So there's about a 31% chance that when you flip a coin 5 times, that exactly 3 of the 5 coin flips will be tails. All right, so maybe a little bit too much information, but that is the formula for a binomial distribution. Now, this, again, I didn't study my notes ahead of time to know exactly what I should expect on my next screen. Maybe I should flip ahead and look. But what I want to say is that you can just do this on your TI-84 if you have a TI-84, or TI Inspire if you're unfortunate enough to have to use that calculator that we have available for our students, using the binom PDF function. So the binom PDF function does all of this for you. Binom stands for binomial. PDF stands for probability distribution function. Right? And it needs to have some numbers in order to do the calculation. So you select that function. It needs to know, I always forget the order that I have to put this in. It needs to know n. So you put n first, I'm pretty sure. I'll double check just to make sure in a second. You put n first, which is the number of trials. And then you might think, oh, you put x next, right? How many successes you want out of those n trials? Actually, no. And there's a reason why they saved that one for last. The next one you want to put is p, the probability of a success on any given trial, right? And that's what's going to go here. And then you put x last, right? Which is the number of successes out of those n trials. And you might say, well, what about q? It can calculate q with p, right? q is equal to 1 minus p. So if you tell it the value of p, the calculator is going to figure out what q is equal to without you having to type it in for it, okay? So all you have to do is tell it what p is equal to. From that, it can figure out q, and then it needs to know n and x, and then it throws all those numbers into this formula and does the calculation for you. So let me just double check to make sure I have the inputs in the right order. And I'm going to use my calculator I have with me. I will record a separate video to show you how to use the calculator to access Binom PDF. I can't really do it the way I'm set up right now, but I have a different setup I use to just show the calculator, and I'll do that. I haven't done it yet, but there should be one for you to watch at some point. All right, so Binom PDF. I go to distribution, And you have to scroll down a ways. It's not at the top. All right, it's option A on my list under distributions. Then I'm going to type in let's just confirm our answer in this case. So for the 3 tails out of 5 coin flips, what I would type in is Binomial PDF. And then I would type in 5 for the number of coin flips. 1/2, you can do fractions there, or you can put 0.5 if you prefer. 1/2 for the probability of a success on any one coin flip, right? So 1/2 chance of getting tails. And then I wanted 3 tails. I wanted 3 successes out of those 5 coin flips. Let's just make sure I did the problem right. So 5, comma, 1/2, comma, 3. And I got the same answer. Right? Comes out as 0.3125, just like we got before. All right. And so that's what you would do on your calculator to get the same result. All right, let's see what this next one is. Okay. All right, so we kind of just broke that down already. So this is what we just did on the last screen, so I'm not going to go back through that again. But it explains why the formula looks the way it does. And this is your N choose C, sorry, not choose C, your N choose X formula that we just talked about. This one is written backwards from what I wrote. I put X factorial first and then N minus X, but because you're multiplying, it doesn't matter the order you put those in. So it's really the same thing we just talked about. So let's find the probability. Let's see, where do I talk about? Okay. And I already just talked about this, that you can find the probability in a binomial distribution using the TI-84 by doing Binomial PDF. And there's probably also websites. So if you don't have your calculator handy, but you got your phone, just do a Google search of binomial distribution calculator, and you will get a website where you can type in N and P and X, and it'll do the calculation for you as well. So if that's, if you're working on the homework and you don't have it handy or something, now when you take the test, you're not allowed to access the internet like that, so you need to make sure you have your calculator nearby to do that calculation. All right, so let's do this one with the technology, right? Without using the formula. So find the probability of getting heads twice when flipping a coin 4 times, right? So in this case, N is equal to 4. The number of successes is 2, right? X is equal to 2. I'm not writing 2s very good today. Let's try that again. And the probability of a success, the probability of getting heads on any one coin flip is 1/2. And so we could type that into Binomial PDF. We'll have 4, comma 1/2, comma 2. So if you're watching this at home, maybe if you have your calculator nearby, why don't you go ahead and try to do the calculation as well to make sure you can find that function and that you're typing it in correctly and that you're getting the answer you're supposed to get. So let me find out what that answer should be. So 4, comma 1/2, comma 2. Close the parentheses, and I'm getting, you might think, oh, it's 1/2, right? Because 2 out of 4, that's half the coins being heads, should be 50%. Not the case. It's 0.375. Okay. So about a 38% chance that when you flip a coin 5 times, sorry, not 5, when you flip a coin 4 times, that you will get heads twice out of the 4. Again, that's exactly 2 heads out of 4. So if you flip it and you got 3 heads and 1 tail, that doesn't count in this probability. We're not including that outcome in this probability calculation. We're talking about exactly 2, not 2 or more. Right? So a lot of times I think when people think, oh, I'll flip a coin and what's the chance I would get 3 heads out of, 10 coin flips or whatever, they're thinking 3 or more. As long as they get at least 3, they're happy that they got the number that they wanted. But we're talking about exact, right? Exactly that number, not more, not less, exactly that number. So that changes the probability a little bit. All right. So some of the problems on the homework will just give you these numbers. And while you might get a little annoyed, especially as we're going forward in this course, because we're going to be seeing some more and more, complex type of questions. They give you the background information on the study that's being done, the thing that they're looking at, what the claim is about. There's always some background information about the numbers that we're working with. And you might find that a little annoying at times, but then when you see problems like this, I don't know, I kind of miss it. I kind of feel like, I wish I knew more about what's going on with these numbers. It really makes it a very boring, uninteresting problem when you just strip it down to just, there's 9 trials, 2 successes, the probability of a success is 35%. but it doesn't tell you anything about the background for those numbers, right? So assume that a probability yields a binomial distribution with a trial repeated n times. In this case, n is 9. Use the binomial formula or technology, which is what we're going to do, to find the probability of x successes given the probability p of a success on a single trial. Right. Now notice, you gotta be a little careful here, because this is the way that they will often give you the numbers in the problem. But when you go to use Binom PDF, n goes first, so you have 9. Then you put p. So you're not actually going to put these numbers in the same order that they're given to you in Binom PDF, right? We have to put n first, then p, and x goes last. So 2 would go last. So be careful that you don't just automatically take the numbers you're given and put them in Binom PDF in the same order they're given to you, because likely they're not given to you in the right order. So you have to make sure you arrange them correctly. So it gets kind of boring, Now with the formula, it's a little more exciting for me to do that on the video because you have to plug the numbers in, do these calculations. It's kind of boring. I feel kind of bad. I can't really show you, but I'm using my calculator. Maybe I could hold it up to the camera screen, but so this is what, I don't know if you can see that very well. We'll see after I finish the recording, but that's what it looks like in the calculator. And it's doing all the stuff that formula does. It's calculating p to the x power. It's calculating q to the n minus x power. It's finding n choose x, whatever n and x are equal to, multiplying all that stuff together to give you your answer. But the calculator does all the work for us. So I do second distribution. I scroll down to Binom PDF. I'll type in 9, comma, 0.35, comma 2. And I'm getting that and I guess I should maybe be writing this as well. This is the probability of getting 2 successes out of those 9 trials. It's going to be 0.2162. I don't know. I'm just going 4 decimal places for some reason. All right. So about 22% chance for that to happen. And again, it's kind of boring, right? There's nothing to talk about here. It doesn't relate to any particular scenario. So that's just the probability that would happen. Or whatever the success is, whatever the trials are, if the probability of a success on any one trial is 35%, and you want to know the probability of having 2 of those successes out of 9 trials, that probability is about 22%. All right. Same thing on this one. So why don't you give this one a try, because it's really just the same thing. So if you have your calculator handy, or if you want to practice maybe using a website or something, again, you can't do that on the test, but for the purposes of learning, you're more welcome to practice with a website. Do a Google search, binomial probability calculator, type these numbers in, see what you get for the probability. Or again, use your calculator, Binom PDF. All right, so I don't know if everybody, like when I say pause the video, give this problem a try, I'm not sure how many people are actually doing that. But something I meant to ask before you did that was just to get your sense of the situation, to see if it's kind of on point, if your intuition is correct or not. I wanted to ask what you thought the probability should be. Should it be a small probability? Should it be a large probability? Is there a good chance of this occurring, or is there like a small chance of it occurring? And so if you think about what's being asked here, you're having 15 trials, you're doing something 15 times. The probability of a success any one time that you run that trial is just 1/3, 33% chance that the thing you want to happen will happen. And it's asking for the probability that you have 13 successes out of those 15 trials, when the probability of a success on any one of those trials is only 1/3. And so if you think about, well, what would you normally expect? I mean, this probability is 1/3, which means 1/3 of the time the thing should happen. The success should occur 1/3 of the time, right? You're running the trial 15 times. On average, 1/3 of the time the success should happen. So how many successes should you expect out of 15 trials? You should only be expecting about 5, right? 5 would be typical, it'd be normal. Given that the probability is 1/3, 1/3 of the time a success should happen. So 1/3 of 15 is 5. So I would be expecting about 5 out of 15 to occur. So think back to expected value in the previous video in 5.1, right? The expected value here is 5. I would expect 5 successes out of those 15 trials. We're going to talk about how to calculate that before the end of the video, but hopefully that intuitively makes sense to you. So to have 13 successes when you're expecting 5 is very unlikely, right? 5 should be the typical kind of outcome. 5, 6, 7, somewhere in there, maybe 4 or 3, right? Somewhere close to 5 is where you expect the number of successes to be. So to have 13 successes out of 15 trials, when only a third of them should be successful, should be really rare. The probability should be really low. And in fact, that's what you find. So when I do this calculation, my calculator tells me 2.927. You might say, wait a minute, that's a pretty big number. Again, if that's all you looked at in your calculation, and you stopped there and then you said this is your answer, you didn't look far enough, right? For one thing, this doesn't make sense as an answer. Probabilities have to be between 0 and 1. You can't have a probability of 2.9 like this, right? That's not a sensible answer for a probability. So if you look further down on the right-hand side of your calculator, you'll see the e to the negative 5. You cannot disregard that part of the answer. You can't just say, I'll just take the first few numbers I see and that's going to be my answer. If there's an e there at the end of it, that's a really important part of the answer. This means we have 2.927, and there's more after that, but times 10 to the negative 5th, right? That e negative 5 means it's scientific notation. And it's times 10 to the negative 5th, which really affects the nature of this answer. It's not 2.9. Right? If you convert this back to a regular number, it's 0.00002927, right? That decimal place needs to get moved to the right. Sorry, I said to the right. Oh my gosh. It needs to get moved to the left 5 times. Right? So that's 1, 2, 3, 4, 5. So it needs to go here. And you fill in the empty spaces with zeros. So you get 4 zeros, and then those numbers occur. That's the probability of having 13 successes out of 15 trials, when the probability of a success is 1/3. Very, very unlikely. Much, much less than 1% chance. So if you were asked, is this unlikely to occur? Yes, it's way less than 5% chance of occurring. So it meets that threshold of being labeled as unlikely. All right. Okay, so here we have some actual, background information, which makes this problem a little more interesting. A penny slot machine was configured so that there is a 1 in 200 probability of winning the jackpot on any individual trial. So any one time somebody uses the slot machine, they have a 1 in 200 chance of winning the jackpot. If you play the slot machine 5 times, find the following probabilities. Find the probability of exactly 2 jackpots out of the 5 times that you play. What's the chance that you would hit the jackpot exactly twice, right? And so 2. We want to find the probability. So I'm going to do this one first down here. The probability of getting exactly 2, right? So that's n is equal to 2. There's 2 trials. Sorry, not n is equal to 2. What am I saying? X is equal to 2. Sorry for the confusion. N is equal to 5, right? We're playing the slot machine 5 times. That's the number of trials. Hitting the jackpot is the success, right? I don't know why I thought n was equal to 2. That's the success. X is equal to 2. And the probability on any one trial of hitting the jackpot is 1 out of 200. So that's the value for P, 1 over 200. So once you've identified all those values, you can use binom PDF. Right? So we're going to do binom PDF. N goes first, which is 5, not 2. Sorry. I made that mistake. I should probably cut it out, but I've referred back to it so many times, I'm just going to have to leave it in. N is equal to 5. Then we put the probability of a success on any one trial, which is 1 out of 200, 1 over 200. Then we put the number of successes, which is 2. And then that's going to give us our answer. So let's go ahead and do that. Second distribution, binomial PDF, 5, comma 1 divided by 200, comma 2. And pretty unlikely that you hit the jackpot twice in the 5 times that you play. Same kind of answer we just got on that last problem, actually. 2.463. Sorry, I put 2 already. 462. I should put 3 there. Let's undo that. rounded up to 3, times 10 to the negative 4 this time, right? So I had e negative 4 at the end of my answer. So on my paper, I'm just going to write times 10 to the negative 4, which we can convert to a standard number instead of being in scientific notation by moving the decimal to the right. Sorry, I said to the right again. Oh my gosh. To the left 4 times. 1, 2, 3, 4. The decimal goes there. We fill in the empty spaces with zeros. 0.0002463. So that's the probability that if you played the slot machine 5 times, that you would hit the jackpot exactly twice. Now, the next question looks really similar, and some students, when they see a problem like that, now, when you see them side by side, you know you got to do, like, it wouldn't make sense to do 2 again, right? Because we just did that one, right? So if this is part A for your homework problem, and then part B says this, you can't just say, well, x is equal to 2, we'll just do binomial PDF with 2, because you're just going to do the same thing you did in part A. So you know there has to be something different about this. But if you didn't have the part A, if all you had was the part B, it's very common for students to make that mistake. They see the 2, they do binomial PDF with 2, and that's the answer they get, and that's what they go with. But it's not just 2, it's at most 2. So I want to find the probability that if I play the slot machine 5 times, that I would get at most 2 jackpots. Now, at most, the phrasing's a little, uncommon. At least is much more common. So we've seen at least before. We did that in chapter 4. At least means this much or more. So again, what I think of for at least is a carnival ride or a roller coaster ride where the sign says you have to be at least this tall to ride this ride. At least this tall means that tall or taller, right? That much or more. At most is the reverse of that. The only scenario I can think of where you might see the word at most is if you go to a restaurant with kids and you want to get the kids' pricing. They don't even use this language, but I want to say at some point, I do remember seeing that at some restaurant, but most of them will say they have to be 12 or under, but you could word that as at most 12. You can get the kids' pricing if your child is at most 12 years old, which means 12 years old or younger, right? The most they could be is 12 years old, but younger than that, they also get the kids' pricing, right? So at most 2 means the most jackpots you're interested in is getting 2, but less is okay as well. So at most 2 means 2 or less. All right, so at most means 2 or less than. So at most is whatever that number is or less than that number. All right, which means we're interested in the probability of getting the jackpot twice, which is what we did in part A, or just once, right? Because that's less than 2. Or, and this is the one that a lot of students will forget about, not at all, right? It's possible that you play the slot machine 5 times and you don't hit the jackpot even once. That is actually probably the most likely thing to happen, right? That you play 5 times and you get 0 jackpots. And so you don't want to forget that's a possibility, right? So hitting the jackpot, you could hit it twice, you could hit it once, or you might not hit the jackpot at all. And there is a probability associated with that as well, right? Now this is an or, right? 2 or less, 2 or 1 or 0, which means we use the addition rule. So we can calculate this probability by just, we can calculate the probability of at most 2 by calculating the probability of these individually and adding them together using the addition rule because it's an or, right? So it's the probability of getting 2 jackpots plus the probability of getting 1 jackpot plus the probability of not hitting the jackpot at all. Now, the addition rule has that extra term of minus the chance that they could happen at the same time. But with these binomial questions, those things can't happen at the same time. You can't play the slot machine 5 times and get both 2 and 1 jackpots at the same time in those 5 trials, right? You either hit the jackpot twice or you just hit it once. Again, because we're talking about exact values, right? So either you have the jackpot exactly twice or you have the jackpot exactly once, but you can't have both at the same time. You can't have the jackpot exactly twice and exactly once, the same 5 times, how do I want to say that? In the same 5 time, that doesn't sound right, during the same procedure, right? The procedure being playing the slot machine 5 times. You can't hit the jackpot both exactly twice and exactly once in that same procedure. Right? So it can't happen at the same time, so you don't have to worry about subtracting out. What I'm trying to say is that these are mutually exclusive, right? They cannot happen at the same time. So, now, how do I calculate this? Well, you could do what we did in part A, but 3 different times. So here's one way of doing this, and I'm not recommending this because this is the most tedious way to do it. There are faster ways for us to get these answers. So I'm going to write it down, but I would, and again, it's what you're comfortable with, if this makes more sense to you, because some students, the other methods I'm going to show you, some students are not comfortable with it. They feel like they're not quite sure exactly how it works, and they're afraid they won't get the right answer if they try to do it that way. So I'm showing you this first method. It takes the longest to get through, but you might feel more comfortable with it, and that's fine. Take the extra time to make sure you're going to get it right. Do it the way that you feel makes the most sense to you, right? And that way is just calculate each of these separately using Binomial PDF, right? So I could do this one, Binomial PDF. Let's try that again. With n being 5, the probability of a success being 1 over 200, and having 2 successes for this one, right? And then to that I would add binomial. I'd have to do my calculator again. So what I'd have to do is do this calculation, write down the answer, which we already have, right? It's 0.0002463. Right, so you do this calculation in your calculator, you get that answer. Write it down on your paper. Then you have to do the probability of getting exactly 1 jackpot, which is another binomial PDF with 5 trials, 1 out of 200 success. And this time, this number of successes is just 1. Sorry, this looks like a 12 over here now that I'm looking at it, so it's kind of bugging me. So that's just 2 there. And then you'd have to find what that is from your calculator, which I'll do in just a second, but you'd have to run the binomial PDF function in your calculator again with these numbers, with the number of successes being 1. Get that answer and write it here. Plus, you'd have to do it a 3rd time for 0, right? Binomial PDF, 5 trials, 1 over 200 for a probability of success, 0 successes this time. So run the binomial PDF again with 0 as your number of successes, and you would have to get that probability and write that here. And then you'd have to add up the 3 probabilities. Right? That's one way to approach it, is just calculate that binomial PDF individually for each one. Now, when there's only 3 like this one, you might think, okay, since it's kind of doing what I already know how to do, maybe I'll just stick with doing that. But there can be some problems on the test and on the homework where you might have to do 5 of these or 7 of these. It might say, the number of trials is 15. What's the probability of having at most 7 successes? Then you have to do 7 and 6 and 5 and 4 and 3 and 2 and 1 and 0. You'd have to do 8 binomial PDFs to calculate the 8 different probabilities and then add those 8 numbers up together. It can get really tedious, but if that's what makes sense and you're comfortable doing it that way, and you feel like that's the way that makes the most sense to you, then that's fine. You can do it like that, right? But here's a shortcut, right? There's 2 shortcuts actually, and so I'm going to show you the next shortcut, which makes it a little faster than what we're doing right now. But there's actually an even faster way that's a little more abstract. That the fastest way to do this problem, a lot of students really don't feel comfortable with, but I'm going to explain it to you all the same. So what we could do instead is to find these 3 probabilities, we can do binomial PDF 1 time instead of 3 different times. So instead of having to type in binomial PDF 3 separate times into your calculator, you can actually find all 3 probabilities by running the binomial PDF just once. And the way you do that is you go to binomial PDF, you type in 5 for the number of trials, you type in 1 over 200 for the probability of a success on any one trial, and you don't specify the number of successes. You just leave that number off, right? So instead of putting 2 or 1 or 0, you just close the parentheses after that. So by not specifying the number of successes, it will do the calculation and tell you all of them. It'll tell you the probability for 1 and 0 and 2 and 3 all the way up to 5. It'll just give you a giant list, at least My calculator just makes a giant list. Now, maybe the newer calculators format it in a way that's easier to read, but it'll give me a list of all the probabilities for every possible number of successes. And then I can just read it off the list. So I do binom PDF. I do 5, comma, 1 over 200, and I close the parentheses. And this is why we put the number of successes last, because it's an optional input. You can specify the number of successes if that's the only probability that you want, or you can choose not to specify it to get a list of all the probabilities for all the possible number of successes. So it gives you an option. So really the number of successes is optional, but that's the only one. N is required, P is required, but X is optional. You don't have to actually type that into the function. All right, so I hit enter. Oops, I didn't hit enter. All right, and so I'll show you, I don't know if you can see it too well on my webcam, but you'll see the bottom. So I did binom PDF. I didn't specify the number of successes. And I get, as an output, this curly bracket thing with a big long decimal number. But you'll notice at the very end of it, there's a space and another number is starting. Another decimal place with another number. And so I can look at those numbers by hitting my arrow key to the right, and it'll scroll over and show me the rest of the numbers. Now what you have to know is what those numbers are telling you. So the order that the probabilities are given in is starting from 0 successes on up to n successes. So for this case, n is equal to 5. So the first probability is for 0 successes. The second probability in the list is for 1 success. The third probability in the list is for 2 successes, on up to 5 successes, right? And so the first one is for 0, which is this one right here. So that's going to be 0.975. 2. I'll just go 4 decimal places. All right. So notice how likely that is. That if you play the slot machine 5 times, there's a 98% chance that you don't hit the jackpot at all. That's the most common outcome from playing the slot machine 5 times. That you just don't get the jackpot even once. What's the probability of hitting the jackpot exactly 1 time? Well, I'm going to scroll over to the right. So let me show you kind of how that looks. All right, so I'm hitting the right arrow. It's sliding over, showing me the next number. And I find that it's 0.02450. All right. That's the probability that if you play the slot machine 5 times, you get exactly 1 jackpot out of those 5 times. It's unlikely, but it's not such a bad probability. It's about 2.5%. Right, so you have about a 2.5% chance of hitting the jackpot once if you play 5 times. All right, and to hit the jackpot twice, very, very unlikely, right? Much less than 1%. And now, so I did the binom PDF once, got all my probabilities from that list, wrote down the ones I needed, and I'm going to add these together. Now, I guess I didn't scroll over, but I already knew the probability for exactly 2 successes, but just to show you, it's the same, it's in the list as well. So the next one over would be for 2 successes. The most common mistake students make with scrolling through the probabilities like this is forgetting that the first probability is for 0 successes. A lot of people start by assuming it's 1 success, 2 success, 3 success, but don't forget it is possible to have 0 successes. That's the lowest number that you could have, and that's the first probability you're given in that list. All right. Then I just add all these up, right? And I'll get an answer. I'll just plug those 3 numbers into my calculator, add them up, get my answer that way. But there is actually an even faster way to add up those probabilities. And you might have noticed it on your calculator already without, you might not really have understood what it meant, but you could do this. Binom CDF. So underneath binom PDF is a function called binom CDF. That stands for binomial cumulative distribution function. And if you remember, like cumulative frequency distributions back in chapter 2, what you're doing there is you're adding it up as you go. In this case, we're going to add up the probabilities as we go. So if I want to have the probabilities from 0 to 2 added together, binom CDF will do that for me. So instead of me having to calculate the probabilities individually, either by separate binom PDFs or even by this one that lists them out. I'm still having to find each one separately and then add them together manually. Binomial CDF will do all that for you. It'll calculate those probabilities and add them for you. So you really don't have to do anything except type in Binomial CDF with the right numbers, right? So Binomial CDF will type in 5 for the number of trials, 1 over 200 for the probability of a success, and we're going to type in 2. So this time you want to specify the number of successes, and that tells it how many probabilities to add up. So for Binomial CDF, at least for my calculator, it starts with 0 successes and adds up to whatever number I put in. So this is going to add up the probabilities for 0, 1, and 2. It goes all the way up to 2, adds those probabilities together for me, and gives me the answer. All right, so I'm going to do Binomial CDF. Now I think the newer calculators actually let you choose the range. So on the old calculator, you were forced to go from 0 up to whatever number you typed in. You had to go, that was the only direction to go, and you always had to start with 0. I think the newer calculators will let you pick that minimum value and that maximum value. So maybe I shouldn't call it minimum and maximum value, but they let you pick the lower bound and the upper bound in this case. So if you wanted to find the probabilities from 2 to 4, the newer calculators will let you type that in. Add the probabilities for me from 2 successes to 4 successes, and it'll add the ones you specify through that range. But on the older calculators, the range was always 0 to whatever number you specified. But that's exactly what we want. We want to add up the probabilities from 0 to 2. So this is going to do exactly what I need it to do. And so we are going to get Binomial CDF 5, 1 out of 200, 2, and we get 0.99999. There's even more than that. It's crazy because like if I decide to round it here, this whole thing just rounds up to 1. So it's almost certain that if you were to play the slot machine 5 times, that you would have 2 or less jackpots. It's not 100%, but it's practically 100%, right? It's 0.999999. If Math Excel, and I keep saying Math Excel, if my stat lab tells you to round this number to 3 or 4 decimal places, if you have to round this, this rounds to 1. And that's what you would type into Math Excel. That's what you type into my stat lab. Sorry, we used Math Excel before with other classes, so we were using it for statistics, but we've actually just recently switched to my stat lab, but you know, old habits die hard. I keep referring to it as Math Excel. All right. So this is the fastest way to do it. But like I said, the CDF, there's just so much the calculator is doing for you behind the scenes that students aren't quite comfortable using that and being certain that it's doing the right thing, that it's giving them the answer that they need. And so if you want to have more control over the steps and the calculations, these are your other options. Either do Binomial PDF individually for each probability that you need to calculate, or do the Binomial PDF with the list and write down each probability for the different successes that you're working with. But if you want the quickest way possible, Binomial CDF is the way to go if you have multiple probabilities to add up through a range of successes. All right, let's take a look at another example. All right, so sorry, I paused the video for a second just to get a drink, and I'm looking at the time. It's already 1 hour and 15 minutes, and I'm really sorry. I wasn't even paying attention to it. I was kind of noticing, like, man, it's kind of, my chest is kind of hurting a little bit from all the talking I'm doing, and that would explain it. Same problem, but this time we want to find the probability of at least 4 jackpots. So this time we're going back to the at least terminology. So the probability of having at least 4 jackpots here. So remember, at least means, think about the carnival ride. At least this tall means this tall or taller. So it means that much or more. So at least 4 means 4 or more. Now, because we're only playing the slot machine 5 times, right, n is equal to 5, there's not much more than 4 that you can go, right? So 4 or more just means either winning the jackpot 4 times or 5 times, because if you're only playing the slot machine 5 times, you can only win the jackpot 5 times. You can't win it more than that. So for this problem, 4 or more is just, so whenever you do the at least, you start with that number and you go up to whatever n is equal to, because that's the most you could possibly have, right? So just, in this case, it's just going to be 4 or 5. So for this one, given my calculator's limitation, Binom CDF may not work as well, because Binom CDF doesn't go in this direction. It doesn't go from 4 up. It always goes from 0 up to a number. And so I can't start at 4, for example. I have to start at 0 with Binom CDF. So for this one, I think what I will do is I'll find the probabilities of these two separately using Binom PDF, since there's only 2 of them. Now, if there was more than 2, if there's like 4 or 5, there's another workaround to my calculator's limitation. It's a little complicated. But if you have a newer TI-84, you might not have that limitation, and you might just go with Binom CDF again. And if you can type in from 4 successes to 5 successes with Binom CDF, that would be the best way to go. That'd be the quickest way to do the problem. But I don't have that newer version of the calculator, so I'm going to do Binom PDF. But I'm not going to specify the number of successes. I'll just get the list. I'll scroll to the end of that list to get the probability of 4 and the probability of 5. It'll be the last 2 numbers on that list, right? So 5 trials, 1 out of 200 probability of success. And then I'm not going to type anything else in. And by the way, we're getting pretty close to being done. Once we get past this slot machine problem, we have to talk about the mean and the standard deviation. And then we will we'll be done. That's the last topic. So we're pretty close. Distribution, Binom PDF, 5, 1 out of 200. Scroll, scroll, scroll. Now this one gets a little confusing because there's a lot to scroll through. But since 5 is the most we can have, 5 would be the last probability. So I'll start with that one. I'll just go to the very last number in my calculation. It's 3.125 times 10 to the negative 12th. Right? Obviously, you should be expecting that. The chance of hitting the jackpot all 5 times that you play is going to be astronomically small. That sounds kind of funny to say, astronomically small, but phenomenally small, right? It's a very, very, very unlikely thing to happen. Now, the probability of 4 is going to be the probability just before that last one. So when I scroll back to the left, I see this number next to the last one, which is 3.109375 times 10 to the negative 9, which is significantly different than like negative 12 and negative 9. That's a 1,000-fold difference between the two, right? And we want to add these together. I'm sorry the numbers kind of ran together there. But we want to add these probabilities together. So I'm going to type them into my calculator. 3.109375. I'll just keep all those decimal places. E to the negative 9 plus 3.125 e to the negative 12. And you'll notice that the second number, because it's 1,000 times smaller in magnitude than the first number, doesn't really change this first number very much. It does a little bit, but not like, well, I guess it kind of does. It's still 3.1. But then it's going to be 125 times 10 to the negative 9. So it really didn't move it much from where this one already was, because this isn't really going to be adding much to that. And so that would be my probability. If MathExcel, I keep calling it MathExcel, if my stat lab asks you to round this number to like 3 or 5 or 7 decimal places, it rounds to 0. It's practically impossible to win the jackpot this much. So this rounds to 0 if it asks you to round it. Okay, so that's the probability of hitting the jackpot at least 4 times. That means 4 or 5. What's the probability of never hitting the jackpot? Well, we actually already calculated this, right? It's the probability of hitting the jackpot 0 times. So really, we already did that, right? But let's see. It's no, I already did a calculator. I was going to say I still have the list up, but I forgot I added those 2 numbers together. So let's go back. Sorry, I went too far. This right here. So this is it. The probability of 0 successes. That's never hitting the jackpot. It's 0.9752. Right, so we already figured that one out. 0.9752. All right. Now keep that in mind for the next question, which is, what is the probability of hitting the jackpot at least once? So this is reviewing a topic from chapter 4. Now it's the at least again. So at least once. So let's just put 1 there. At least 1. So what's the probability that the number of jackpots we hit is at least once? I was trying to just say one there, but once still makes more sense. This means one or more, right? And if you want to do this problem the way we just did the last at least problem, you have a lot more probabilities you have to consider, right? Because one or more means we're going to have 1 or 2 all the way up to n, right? Or 3 or 4 or 5. Which means I'd have to add the probability of 1 plus the probability of 2 plus the probability of 3 all the way up to 5, right? I'm already tired of writing this out, and I'm not even actually going to do these calculations. That's the worst way to go about it. The best way to go about it is to use what we learned in chapter 4, which is the probability of at least 1 is 1 minus the probability of none. Right? So that's something we learned in chapter 4. These are complements. The opposite of at least 1 means none at all. And so that one we already calculated. The probability of none was 0.9725, was it? 9752. Got my numbers backwards. 9752. So I take 1 minus that, 1 minus 0.9752, to get the probability that I hit the jackpot at least once, which is 0.0248. Which you'll notice is not much different than hitting the jackpot exactly once, is what I was going to say. I forgot what I was about to say there. So the probability of hitting the jackpot exactly once, okay, what did I do? Okay, I'm hitting the wrong button again. The probability of hitting the jackpot exactly once is 0.0245, right? So about 2.5%. This is 0.0248, right? So slightly higher. So the probability of hitting the jackpot exactly once is 0.0245. The probability of hitting it once or more is 0.0248. So it's just a slightly more likely thing to happen, but almost negligible, right? Okay. Is it likely to never hit the jackpot? Yes, right? Because never hitting the jackpot, there's a 98% chance of that. It's by far the most likely thing to happen. Okay, let's move on because this video already is way too long. I probably spent too much time talking about that binomial formula, which I like to do because it's an interesting formula, and the reasons for why it looks that way to me are interesting to understand. So I'm sorry I made you have to go the way. I guess you didn't have to. You could have skipped past it if you wanted to, I guess. All right, so the mean and the standard deviation for a binomial distribution is super duper easy to calculate. So easy, in fact, that students like it so much that they want to use these formulas for everything else. And you can't do that. So students will have this formula on their formula sheet when they take the test. And they use, anytime it asks for a mean, they use this formula. But you can only use it if what you're working with is a binomial distribution. It only works on binomial distributions. So do not use this formula to calculate the mean or the standard deviation for other types of probability distributions. It doesn't work. Only for binomial distributions. So please keep that in mind. And this is why binomial distributions are nice. It's nice to be able to construct these and to identify when they're occurring, because then we get these nice, easy formulas for calculating the mean and the standard deviation. But if it's not binomial, you can't use these formulas. You have to use the methods we talked about in 5.1, which were definitely a lot more tedious. The calculations were more complex and took a lot more time. But there's nothing else for it. That's the only way to do it. You can only use these formulas if it's binomial. So I just want to say that one more time to really emphasize that, because no matter how many times I say it, I will still have students use these formulas on other probability distributions where they don't apply. Assume a procedure yields a binomial distribution. Use the given values of n and p to find the mean and the standard deviation. And of course, once you have the mean and the standard deviation, then you can find maximum and minimum usual values. And so it asks us to go ahead and do that as well. Right. So to find the mean of this binomial distribution, again, it's kind of a sad problem, right? You really start to miss that background information that brings the numbers to life, right? Because like these numbers are just, they're meaningless. They don't have any kind of meaning to them whatsoever. But we can still do the calculations, right? So because it's binomial, the mean will just be n times p. Right, very simple, easy formula. N in this case is 152 times p, which is, I'll just put a 0 there, 0.2, So here are my two numbers. I'm just going to multiply those together. 152 times 0.2, which is 30.4, which again is your expected value. So out of those 152 trials, you would expect to have 30.4 successes out of the 152 trials. So that'd be the number of successes you should expect to occur, right? Given that probability of 0.2. Now the standard deviation is a little more complicated. You got to do the square root of n times p times q. They didn't tell us what q is equal to, so we have to remember that q is 1 minus p. Right? It's the complement of p. So to calculate the probability for q, it's 1 minus p. 1 minus 0.2, which is going to give me 0.8. The probability of success is 20%. That means the probability of a failure is 80%, right? Because it's either success or failure. And now we have all the numbers we need to plug into this formula. So let's find that standard deviation. It's going to be the square root of n, which is 152, times p, which is 0.2, times q, which is 0.8. Now, mathematically, I kind of struggle with this because, like, I don't know, maybe I kind of got in a lazy habit. But when I'm like right here, I wasn't going to write the 0 because it's really mathematically not necessary. 0.2 is the same as 0.2. But I had a professor that I worked with who's since retired who pointed out to me that the reason you put the 0 there is to make the number easier to read. It doesn't have to be there mathematically speaking, but without it, sometimes it's hard to see the decimal place. So by having the 0 there, you know there has to be a decimal place. Otherwise, the 0 wouldn't be necessary at all. There would be no, like the 0 wouldn't even be there if there wasn't a decimal place. So, because if I write just 0.2 and you don't quite see that, you could easily think of that as just the number 2. But if I put 0 in front of it, there's no reason if the number was 2, you wouldn't have a 0 in front of it. The only reason there would be a 0 is because of the decimal place. So it kind of draws your attention to that. So I'm trying to get in a better habit of putting a 0 in front of my decimals. All right, if there's no other number that belongs there. So plug that into your calculator, right? We have 152 times 0.2 times 0.8. And then don't forget, take the square root of that result. And you could have probably typed that in all at once without having to do it separately. But I like to do the multiplication first, then apply the square root. And I'm getting I'll just go 2 decimal places. I don't know, 4.93. All right. And that'd be the standard deviation. Maybe 1 decimal place is more appropriate because my mean is only to 1 decimal place. So let's keep the standard deviation to 1 decimal place also. All right. For the next part, which is to find the minimum and maximum usual value. So the minimum usual value is the mean minus 2 times the standard deviation. Let's try that again. Which is going to be 30.4 minus 2 times 4.9. Which again, I can do in my calculator. 30.4 minus 2 times 4.9. 20.6. So whatever this procedure is, the expected value from running 152 trials is to have 30.4 successes. That's what we would expect. That's the average outcome that should occur, right? So if we were going to do this procedure a large number of times, that we're going to have 152 trials multiple times, and we took the successes each time from those 152 trials and averaged them together, the average should be around 30, right? That's what the expected value means. However, the minimum usual value is 20.6, which means that, if we only had 25 successes, that would not be unusual to see. That would not be uncommon. 25, it's not the expected value, but it's, it's a typical value. Anything down to 20.6 would be considered typical. But if I only had 15 successes out of the 152 trials, that would be unusual because that goes below the minimum usual, right? So this is the smallest number that I consider to be usual or typical. Anything below that number is unusual or atypical for this situation, right? So again, if X was 15, having only 15 successes would be considered unusual given these numbers, right? Because 20.6 is the lowest I would consider to be usual, and 15 is lower than that, right? For the maximum usual value, it's the mean plus 2 times the standard deviation, which is going to be 30.4 plus 2 times 4.9. Just scroll down a little more so I have some room to write. So 30.4 plus 2 times 4.9, which will be 40.2. I'm just going to switch to a different color. 40.2. That is the highest number that I would consider to be normal or usual or typical. Anything higher than that would be abnormal, abnormally high, unexpected, atypical, unusual. I don't know other words that mean the same thing. So if I ran 152 trials and I had 50 successes, that would be unusual because 40 is the most that I would consider usual. Anything over that becomes unusually high. It's an unusually high number of successes, right? So again, if you think of it on a real number line, we have 20.6, we have 40.2. That's my minimum usual value. That's my maximum usual value. Anything in between would be considered usual or typical or normal. So if I had 35 successes out of 152, I'd say, well, that's about what you get when the probability is 0.2 for a success. 35 is not out of the ordinary at all, right? 39, it's getting up there, but I would still say that happens, right? That's going to happen pretty frequently given these numbers. But once I cross that threshold of 40.2 and I have 41 successes out of 152 trials, that's unusual given that the probability of success is only 20%, right? It's unusual to have that many. So here's what I would consider usual or typical for the number of successes. Anything below that or above it would be considered unusual. Oops, I'm leaving out letters here. Okay, unusual, and this one's also unusual. All right. Okay, sorry, I should have used different colors there, but hopefully we've gone over that a couple times, I think, already, so hopefully by now it's making sense. All right, I have 2 more examples. I'm sorry, this is already an hour and a half. I feel really bad. Now, I will say in my defense that these used to be 2 separate sections, and they've lumped them together into a single section, which they did that to me in chapter 4 with addition and multiplication rule, putting those into one section. So it's like 2 lessons in one. That's kind of why it's about twice the length that it should be. All right. Mars Inc. claims that 24% of its M&M plain candies are blue. A sample of 100 M&Ms is randomly selected. Find the mean and the standard deviation for the number of blue M&Ms in such groups of 100. Would it be unusual to find 12 blue M&Ms in a group of 100? What would finding 12 blue M&Ms out of 100 indicate about the Mars Inc. claim? All right. So we're going to assume their claim is true, that indeed 24% of their M&Ms are blue. And so the probability when I choose an M&M out of the bag that it's blue is going to be 24%. And that's the thing we're going to consider a success. Again, not that blue M&Ms are better than other M&Ms. We're not saying that by calling it a success. It's just that's the thing we're measuring the probability of. So that becomes the thing we call a success, right? So when I choose an M&M, the probability of that one M&M being blue is 0.24. That's the probability of a success on any one trial, on any one M&M. And so that's the value for P, right? We are going to get a sample of 100 M&Ms. So we're going to run 100 trials, right? Because we're checking the color of 100 different M&Ms. That's 100 different trials. The probability that any one of those M&Ms is blue is 0.24, right? And we want to know the mean and the standard deviation based on those numbers, right? So let's go ahead and find that first. So yeah, so I was going to say, I couldn't remember, but yeah, it does say that. So the mean, remember the formula, because it's a binomial distribution, it doesn't say that in the problem, but there's 2 outcomes. Now you might say, wait a minute, there's not 2 outcomes. M&Ms can be blue, they can be orange, they can be green, but we're not recording the color of the M&Ms in this case. We are just only recording whether it's blue or not blue. So either the M&M comes out blue or it wasn't blue. That's binomial, right? That's 2 different outcomes. So as long as you think of it that way, and you're not recording the specific colors, but just whether it was blue or not, it fits the description of a binomial distribution. And so we can use this formula. N is equal to 100, P is equal to 0.24. I guess I'll put both of these in parentheses. And so the mean here is going to be 24. So this example is nice. I borrowed this from my colleague. These are nice numbers, right? Because 100 times 0.24 is just an easy calculation to do. So remember, your mean for a probability distribution is also, this video has gone on for too long, is also your expected value. So if I have a pack of 100 M&Ms, I would expect to find on average 24 of them to be blue if Mars Inc. is telling the truth about that proportion, right? Now, if I found 22, would that be unusual? No, because, I'm sure we're about to find out, but I'm sure 22 is within the usual range. But just on average, opening up multiple bags of 100 M&Ms, if I count the number of blue ones, I would expect on average to have 24 in each pack. I might have a little more here, a little less here, but when I average it out, it should be about 24 per pack. All right. The standard deviation is the square root of N times P times Q, which means I need to find Q. Right? So let's go back up here, I guess. P is 0.24, which means Q will be 1 minus that. It's going to be 1 minus 0.24, which is going to be 0.76. Now, see, I'm going into my bad habit of not putting zeros in front of those decimals. I'm apologizing for that. All right, should have done that, especially here. This one's where it gets kind of hard to read. So 0.76 is the value for Q. So keep that in mind because it's going to be off the screen. So we're going to have the standard deviation equals the square root of N, which is 100, times P, which is, let's do 0.24, times Q, which is 0.76. And get that fraction bar, that square root bar all the way across the whole thing. So let's plug this into our calculator. 100 times 0.24 times 0.76. And then we'll take the square root of that number. And this one, it's hard to make it work out nice with that square root. So you're going to get let's just go one decimal place, 4.3. So the standard deviation is 4.3 for this binomial distribution. So with that, I can find the minimum and maximum usual values. Now, I don't think I need both. It doesn't ask me to find both. It just says find the mean and the standard deviation. And then it asks me a question. Would it be unusual to find 12 blue M&Ms? So I don't really need the maximum usual value to answer that question. And now if it bothers you to only find one and not the other, then go ahead and find both. But 12 is below the mean. So my only concern is 12 below the minimum usual value? I don't have to worry about this being above the maximum usual value, right? Because 12 isn't above my mean. It's below my mean. So the only way 12 could be unusual is if it goes too low, below my minimum usual value. So that's the only one I really need to find. And I think that's what I'm going to do because I really don't want a 2-hour video here, and we're getting really close to that. So the minimum usual value is the mean minus 2 times the standard deviation, which is going to be 24 minus 2 times 4.3. I'm sorry, that didn't write all the way completely. All right, okay, so I'm plugging that into my calculator. 24 minus 2 times 4.3, and I get 15.4. That is the lowest number of blue M&Ms out of 100 that I would consider to be normal given the numbers that we were provided. Right? Anything below 15.4 is unusually low for the number of blue M&Ms in a pack of 100. Right? So 12 would be unusual. Right? So again, if you think of the real number line, the minimum usual value is 15.4. I don't know why it does that. 15.4. I don't know the maximum. I didn't calculate it. I don't need it for this problem. Right? But it's some number up there, right? And this is the range that we consider to be usual. So any number of blue M&Ms in this range would be considered normal or typical given the numbers that we were provided, and it wouldn't raise any eyebrows, right? But if you have a number of blue M&Ms that goes outside of this range, so let me pick a different color this time. So in this area here, this is considered unusual. Same over here, whatever that cutoff value is, this is the maximum usual value, whatever that happens to be. If it goes above that, that would also be considered unusual. And this should make us raise our eyebrows, right? We should question the information provided by Mars Inc. because we assumed what they told us was true. We said, okay, you're saying there's 24% blue M&Ms? Okay, we'll run the calculations on that. And given that claim that they're making, we would expect to have 24 blue M&Ms per pack on average. And we know that there can be some variation. Sometimes it won't get exactly right. But even given that variation, we would not expect the number of blue M&Ms to dip below 15.4, right? So anything down to 15.4, we can write off as just normal variation, given that there's 24% blue M&Ms. But if it goes below that, that's unusual. And that really calls into question the claim they're making, that 24% are blue. Because if that's true, we shouldn't be seeing 12. Or if we do, we should only see that only rarely. So it could be the case that we just had a really unlucky pack of M&Ms and we just happened to get 12, right? Which is unusual, right? And we just had an unusual pack. That can happen rarely, right? That's, again, how often is it unusual? It should only happen less than 5% of the time, right? So maybe this is one of those 5% of the times where we just get this unusual number. But if we run the experiment again and we buy another pack of 100 M&Ms and we get 12 again, that is hard to chalk up to chance, right? What's the chance that you would get a rare event twice in a row? And that really would cause us to question the claim that Mars Inc. is making about the number of blue M&Ms in their packs. So to answer the question, the answer is yes, right? Would it be unusual? Yes. We found that it was unusual. What would finding 12 blue M&Ms out of 100 indicate about the Mars Inc. claim? You wouldn't, so this, again, you have to be careful with statistics. You can't state anything with 100% certainty. So we wouldn't say, oh, Mars is lying. It's not 24%. They're lying about that. We have to be a little more nuanced than that, right? So we have to say it's questionable, right? That it's suspect. It's suspicious would be maybe more diplomatic terms to use. It's not consistent with the statistics that we're doing here for that claim to be true. So I would just say it's suspect or questionable, whatever wording you want to use. All right. Say about the claim. The claim is suspect. The claim is questionable because it would be unusual to only have 12 blue M&Ms if there should be 24% M&Ms in each pack. All right. Last question. Can we keep it under 2 hours? Let's see. Oh, it's a long question too. Okay. In a past presidential election, the actual voter turnout was 61%. In a survey, 1,002 subjects were asked if they voted in the presidential election. So I think it's pretty clear what's going to happen here. N's going to be the 1,002. Find the mean and standard deviation for the group of actual voters in groups of 1,002. And so we're going to use this as our value for P. And again, this is it doesn't say it's binomial. But of course, if it's in this section, you can probably just kind of assume, unless they're asking you to think about is it binomial or not. When they give you a problem and they say find the mean, you can probably just assume it's a binomial distribution. But if you think about it, like the key thing that you want to look for is, are there two outcomes? And there is. Either the person voted or they didn't vote, right? There's two outcomes there. So now, are they independent? Maybe not, because like one person voting might influence somebody else not to vote. But we're not going to dig that deep into the scenario. So we're just going to follow the directions here. We're going to assume it's binomial, find the mean and the standard deviation. So keep those numbers in mind as we do these calculations for part A. The mean is going to be, how about we just do this? This will save me some time on my video. You calculate the mean and the standard deviation. I'll pause my recording and do the same. And that way you don't have to sit there and watch me do the calculation. And then you can check to see if you came up with the right answer. Okay, so the answers you should have come up with for the mean is 611.22. And for the standard deviation, it's 15.44. Right now, to find the standard deviation, you have to also calculate Q, which is 1 minus P. So you should have found Q as 0.39 to do that calculation. In the survey of 1,002 people, 701 said that they voted in the last presidential election. Is this result consistent with the actual voter turnout of 61%? So we're trying to see if what people are saying is consistent with what we actually know happened. Because sometimes people might lie. Somebody maybe didn't vote, but they're ashamed to say they didn't go vote, so they're going to tell the survey people I did vote, even though they really didn't. So we just want to know, is the result we're getting from the survey consistent with what we actually know about voter turnout? Now, to answer that question, again, we're going to find the minimum and maximum usual values. So why don't we go ahead and pause the video again, find the minimum and maximum usual value for this situation, and then determine if 701 is usual or unusual based on that. All right, so what you should find for the minimum usual value, given the calculations we've done, is 580.32. That's the mean minus 2 times the standard deviation. For the maximum usual value, you should find that the maximum usual value is 642.1. And so that is your range of usual values. Anything outside of that range would be considered unusual. So again, I drew this helpful visual here to help you see that. Here's my minimum usual value. This is my maximum usual value. In between those two numbers would be typical results that you would expect to get, given the assumptions that we've made or given the numbers that we're working with, right? Outside of that range would be considered unusual. So we're being asked if 701 would be unusual for the number of voters out of 1,002. And the answer is yes, that would be unusual, given that we know only 61% of people voted. It would be unusual to have 701 people say that they voted out of 1,002. That's an unusually high number. And so it seems likely that some people are not being honest, right? Because 700's here. So yes, that is unusual. And so we might question, the honesty of the people that are being surveyed, and that they might feel some shame about admitting that they didn't vote. So, all right, so that concludes the video on 5.2. I'm sorry it took so long. That also concludes Unit 2 of the course. And so the next thing you should be working on is getting ready for Exam 2 on Chapter 4 and 5 if you're in my class. After that, you'll be moving on to Chapter 6. So I'll see you in the next video in 6.1.